Hello, good evening all. I am Saurabh and I welcome you to this live session for the NPTEL course IC Engines and Gas Turbines. So in today's session, we will discuss something related to velocity triangles that is very important for any turbo machinery. And we will try to solve some problems related to centrifugal compressors. Okay. So these velocity triangles are very, very important for the analysis of any turbo machinery, right? So let's start. So question number 1, it says that for a given turbo machinery equation, which of the following option is correct for the condition CW2 into R2 is less than CW1 into R1 in torque equation, as in the following, which is as follows. Torque rotor is equal to mass flow rate of the fluid times this term CW2 into R2 minus CW1 into R1. So basically we are given an equation and that equation is for calculating the torque. Okay. And torque is calculated using this equation, that is basically mass flow rate times this term. Okay, this term. Okay, so in this term, CW is basically whirl velocity component, R2 is the radius of rotor. One, there are few suffix, right? 1 and 2. So 1 is basically inlet and 2 is outlet. Okay, so R2 is the radius at outlet and R1 is the radius of rotor at inlet. Similarly, CW1 is the velocity component at inlet and CW2 is the velocity component at outlet. Okay, so these are terms, and in terms of these, these quantities, the equation of torque is given. So we have to tell this for that for a case of for this case, here it is, sorry, that CW2 into R2 is less than CW1 into R1. So this is case for which type of machine? Okay. So before starting, I think we should be very clear about the notation. Okay. So I will quickly draw some, a diagram so that it is clear. Okay. So we know that in a turbo machine, there can be some part that is rotating and some part can be there that is not rotating. So part which is rotating, that is rotor, and another part that is not rotating, that is stator. Okay. So let us say we have a stator, sorry, rotor. And this rotor will have some blades. Okay, it will have some blades. Let us say this is blade. Okay, so I'm sorry for this bad diagram, but so there will be some blades. Okay, and this will be rotating, and this will be rotating. How it will be rotating? Something like this. Okay, this whole thing will be rotating about this axis. Okay, let us say this is the center. Okay, and this is the radius. And this is rotating. Okay, so it is rotating like this, right? Let us say this is our inlet and this is outlet. One is inlet and two is outlet. One is inlet and two is outlet. Okay. So at inlet, what will happen? Since this rotor is rotating, so this blade will have some velocity, right? So this blade will have some velocity and that will be in this direction, right? In this direction, right? So this velocity we call u. Okay, this velocity we call u. This you can call as uh, blade velocity or blade tip velocity or tangential velocity or whatever you know you think is appropriate. Okay, so let us call this u as tangential velocity. Okay, because this will be along the tangent of this rotor, right? Tangential velocity. So please note that this tangential velocity is of the blade. Okay, even if there is no fluid, nothing, and if this rotor is rotating, even then this u component will be there. Okay, and how much this u component will be? This will be, let us say the angular velocity is omega and this radius is r. Okay, this radius is r. Okay, so this radius is r, then u will be equal to r times omega. Okay, so this is the velocity of rotor, the blade. Okay, it has nothing to do with the fluid velocity. Now comes the fluid. Now comes the fluid. Now fluid is moving and one is inlet, as I told, and two is outlet. So if you see in the reference frame of this rotor blade, okay, please pay attention. In the reference frame of this rotor blade, what will happen? The fluid will go tangentially along this blade. Okay, the fluid will go the tangentially along this blade. So this is blade 1 to 2 and this is the tangent, let us say. So fluid will go along this tangent in the reference frame of this blade. Okay, so what I mean is that in a just imagine that you are sitting at this point A, then what you will observe will be like this. You will observe that fluid is coming tangentially. Okay, fluid is going along this blade tangentially. Okay, when will you observe this thing? When you are in the reference frame of this blade. Okay, when you are sitting at point 1. Okay, now this reference frame is not the inertial reference frame. Okay, so what I mean is that this reference frame is rotating. That is not a static reference frame. So someone who is standing on earth, okay, who is at rest, so what he will observe? He will observe the absolute velocity of the fluid. Okay, he will observe the absolute velocity of the fluid. So in that reference frame, in the absolute, let us call that reference frame absolute reference frame, the velocity will be something else, right? So this is the concept of relative velocity, right? So what is the concept of relative velocity? It is just high school stuff. Okay, so if someone is standing on earth, okay, someone is standing on earth. Okay, so this is one reference frame. Okay, and someone who is moving in a cart. Okay, someone sitting in this cart. Okay, so this is another reference frame. Okay, and both of these guys observe some vehicle. Let us say both of these observe a bicycle. Okay, both of these observe a bicycle. Okay, so this is reference frame 1. This is reference frame 2. Okay, so if this bike is going at some velocity, let us say uh, c in this direction. Okay, with respect to road. Okay, so with respect to road, then in the reference frame of this observer who is in rest, the velocity of this cycle will be c. But in the reference frame of this person who is sitting in this car, and this car, let us say, moving at some velocity u. Okay, let us say this is moving some velocity u. Then in the reference frame of in reference frame rf1, the velocity or speed of bicycle will be c only, right? Because it is not moving. But in the reference frame of person who is sitting in the car, okay, so in the reference frame of person who is sitting in the car, let us call that rf2, second reference frame, the velocity of bicycle will be c minus u. Okay, c minus u. And if you want to write in terms of vectors, then these quantity can be vectors. Okay, u vector, c vector. Similarly here, u vector, c vector. Okay, so same thing is happening here. Okay, so same thing is happening here. So someone who is sitting at the blade at point 1, so he will observe that fluid is going tangentially through the blade. Okay, fluid is moving over the blade tangentially, and the velocity is, let us call, v vector. Let us call this is v vector. Okay, this is the relative velocity. Okay, but person who is standing on earth, that will observe the absolute velocity. Okay, so if you want to write the relation between absolute velocity and the uh, so absolute velocity and relative velocity, so from here you can write it like that, that absolute velocity is equal to relative velocity plus the velocity of this reference frame. Okay, so velocity of this reference frame, in our case, it is the velocity of point 1, the tip velocity. Okay, right? So the absolute velocity will be u vector plus v vector. Okay, so u vector plus v vector. So if I draw the resultant at this point, okay, let me choose some different color. So it will be somewhere here. Okay, it will be somewhere here. So how it comes? It is just our well-known parallelogram law. Okay, so this will be the absolute velocity. Okay, maybe it is I should draw it separately. Okay, so I hope this is clear what I drawn. Okay, so the u is the velocity of blade. It has nothing to do with the fluid, and v vector is the relative velocity of the fluid with respect to the person who is sitting at point 1 or the blade. Okay, and this v is the tangential to the blade. Okay, the fluid is moving over the blade, and c is the absolute velocity, right? So if I draw it, separately, and you should observe that u is the tangential velocity. U is the tangential velocity. By what I mean by tangent is that it is tangent of the rotor. Okay, it is tangent of rotor. Okay, this is our rotor, and this is the tangent of rotor. So u is given by r times omega, and r is the velocity. R is the radius at this point 1, and omega is the angular velocity. Okay, so if I draw this diagram separately, it will look something like this. Okay, how it will look like? First of all, let us draw the u. Okay, so u is in this direction probably, right? U is, let us say, this direction. Okay, probably I should use the same color. We have drawn the u in green. Okay, so this is u. This is what? This is the tip velocity or the tangential velocity, tip velocity of blade. Okay, so this is u, right? This is u vector. And then there is relative velocity of the fluid with respect to blade, that is v vector. Okay, so that is that is in some other direction. Okay, so v vector here is our v vector, right? So let us draw the v vector. So v vector is somewhere there in this direction. right? So this is our V vector. And one thing also you should note, that is vectors you can draw anywhere. Okay. When you are adding vectors, let us say uh, you are adding three vectors, A vector plus B vector plus C vector, then you can, translate these vectors, right? You can translate these vectors for addition purpose. Okay. Until unless you are doing something with, sub calculations where the point is important. For example, you are applying some force, then it is important at what point you are applying some force. But you have many forces acting at that point and you want to find the resultant force, and you have many vectors, then for the adding those vectors to find the resultant force, you can translate those vectors. Okay. So what I mean is that this is vector 1, this is vector 2, this is vector 3, this is vector 4. Okay. So if you want to add these vectors, you just write first vector and you take another vector. So in such a way that the tail of the second vector is at the head of first vector. Okay. So like this, you can keep on adding, and finally, whatever you will get, that will be the resultant. Okay. So anyways, so this is V vector. Okay. I have just rearranged. Okay. I have just rearranged. You can see the direction of V I am trying to preserve. Okay. So U vector plus V vector, that will give the resultant vector, that will be the absolute velocity. Okay. That will be the absolute velocity. So this will be the resultant. This will be the resultant. So this is C vector. Okay. So U vector is basically what? This is the tangential velocity. Tangential velocity component. Okay. Basically it is blade tip velocity, right? Blade tip velocity. And V velocity is the relative velocity of fluid. Okay. Relative velocity of fluid, right? In what reference frame? In the reference frame of this blade. Okay. So let me write with respect to rotor or blade. Okay. Whatever. These blade and rotor, they are fixed together, right? And C velocity is the absolute velocity. Absolute velocity of fluid. Okay. Right. So I hope this terminology is very, very clear. This is very, very important because doesn't matter whether you are solving the problem of a what is this, reciprocal centrifugal compressor or axial compressor or any turbo machinery. Okay, these velocity triangles are used everywhere. So this would be very, very clear. Okay. Now, again, one more concept from your high school. We know torque. So torque is basically force. Okay, let us make this something like this. Okay, you have some wheel. Okay, this is the center, and you are applying some force. You are applying some force, and if you can resolve this force along this tangential component and this radial component, and this is, let us say, the radius of this wheel, then torque on this wheel will be what? Torque will be tangential force times this radius, right? And force you can write in terms of momentum. Okay, so the force is basically rate of change of momentum. P is, let us say, is the momentum. Okay, and the torque is basically rate of change of angular momentum. Okay, torque is rate of change of angular momentum, right? So from here as well, you can write it like so. Rate of change of angular momentum. And how do we write angular momentum? Let us say there is some fluid is flowing and you want to there is some fluid. Okay, let's say this is the velocity vector of the fluid, c vector, and you want to write, and dm, let us say, is the mass of this fluid element, and you want to write the angular momentum of this fluid element about this point. Okay, let us say this is O, and if this distance is r, then basically you have to write something like this. Okay, this is, let us say, okay, then you have to find this component, that is tangential component, that you can write as cw, let us say. Okay, and another component will be cr. Okay, so cr is basically radial component of the velocity, and cw is the tangential component of the velocity, or the whirl component of the velocity. Okay, so the angular momentum will be angular momentum of this fluid element will be dm times its velocity, right? Whirl component times this distance r. Okay, so this will be the angular moment of this fluid element. Okay, so what is important? Important is this whirl component. So this whirl component is very, very important. So this is the whirl component of velocity. So whirl component of which velocity? Relative velocity or absolute velocity? Answer is absolute velocity. Okay, answer is absolute velocity, because we are doing all the analysis in the our reference frame, and we are at rest. Okay, we are not rotating, right? So if you want to write the torque on this fluid element, then how will you write the torque? You will have to just differentiate this angular momentum with respect to time. Okay, so the torque is basically a rate of change of angular momentum. If you want to write the torque, so it will be dm, sorry, so torque will be dl by dt. Okay, and let us say mass flow rate is constant. Mass flow rate is constant. Okay, then radius is also constant. Then no, this is, let's say, delta L vector. Okay, this is the will component, will component. Okay, so this thing will be what? This thing will be mass flow rate times rate of change of this, right? CWR, right? Rate of change of CWR. So I think I should make it more clear. Okay, I will write it again. Instead of D, I will make it as del. Okay, so that there is no confusion between differential operator D and, okay, let's say del m. Okay, so angular momentum is del m times CW times R, right? So the torque will be rate of change of this angular momentum, right? So what we should write? We should write d by dt of del m times CWR. Okay, CWR, right? Okay, Now let us say mass flow rate is constant, right? Mass flow rate is constant. So at point 1, at point 1 or at inlet, let us say this thing was CW1 and radius was R1. At outlet, the variable velocity component is CW2 and radius is R2. Okay, and delta M is constant, right? So then that case torque will be given by this delta M times CW2 into R2 minus CW1 times R1, right? So this is change, right? This is change, and divide by delta T. Okay. So now I am not writing dt, right? Because I'm writing in terms of some finite change. Okay. So this is not infinitesimally small. Okay. So what we got mass flow rate times CW2 R2 minus CW1 R1. Okay. Right. So let me repeat. What I have basically done is I have written this term like this. Okay. So delta M CWR at 2 minus CW1, sorry, delta M CW1 R1, sorry, into CW into R at point 1, right? Divided by T2 minus T1, right? So basically this thing I have written like this, right? And that thing I have simplified like this. Okay, this delta M is constant, and we got this. Okay, so the torque is given by what? Torque is given by mass flow rate times CW2 R2 sorry. And what is this? CW2 R2 and CW1 R1, right? So this is the torque. This is the torque. Okay, so that's what it was given in this question. Torque on motor, sorry, torque on rotor, that is mass flow rate of the fluid times CW2 R2 minus CW1 R1, right? So this is the equation for the torque. Okay, and I just explained how it comes. Now what happens? Now there are two types of machine. One is power consuming machines and another one is power producing machines, right? That you have already, that we have already discussed many times, right? So one is power producing machines. So power producing machines are turbine, right? And power consuming machines, are pump and compressors, right? And there are some other machines which for which work done is zero. Okay, for them work done is 0. For example, nozzle. Okay, so in nozzle, work done is 0. So if the TS, okay, the TS, which TS? TS is equal to mass flow rate times CW2 R2 minus CW1 R1. So machines for which TS is positive, those machines are work consuming, right? Power consuming machines. And machines for which TS is negative, those machines are power producing. Okay, right? So in our question, it is given that CW2 R2 is less than CW1 R1. Okay, so this term will be negative. Okay, so in our case, this term will be negative. And when this term is negative, then what we have? We have power producing machines. What we have? We have power producing machines. Okay, maybe I can explain it a little more so then you should be able to appreciate this fact. Okay, so what is power? So power for translational motion, you already know power is given as force times velocity, okay, dot product. So basically what is happening, power is basically rate of work done, and right, and power, let us, how should I, power, let us say P, okay, so power is basically dw by dt, okay, rate at which work is being done, and dw is basically force times displacement by dt, okay, and this ds by dt is basically u. Okay, so this is power. So force times this velocity dot product. This is for the case of, translation. And in rotation, in case of rotation, exactly same thing. Instead of force, we have got torque, and instead of linear velocity, we have got angular velocity. Okay, right? So this is torque. Okay. So torque, I just wrote the equation, that is mass flow rate times CW2 R2 minus CW2 R1. Okay. And if I multiply by this, omega, if I multiply by this omega to get the work done, okay, power, I will write it as W dot. Okay. So this is rate of work done. So we need to just multiply by the angular velocity. Okay, CW2 R2 times angular velocity, that is omega, CW2 R1 times angular velocity, again omega. Okay, and R2 omega is U2. Okay, the blade tip velocity component at exit. Okay, so CW2 U2 minus CW1 U1. Okay, so this is very important equation. Okay. So now from this equation, you can clearly see what you can clearly see, omega, you are multiplying by omega. Okay. Then, sorry. So if this thing is positive, if this thing is positive, so that means some work is being done on the fluid. Some work is being on the fluid, right? So who is doing the work? Your machine is doing work on the fluid. So fluid is basically consuming the work from the machine. Okay. So if this thing is positive, this ws is, this thing is positive, so that means your machine is work consuming, right? So this is the thing. Okay. And if it is negative, then it means your machine is work producing, and work producing machines are turbines. Anyways, so I think now terminology is clear. Okay. And how do we make these velocity vectors? That is clear. Okay. So if it is clear, then we can move forward. Okay. So answer of this question is last part, axial flow turbine. Why? Because option A is compressor, option B is pump, option C is compressor. All these machines are, you know, power consuming, and only turbine is power producing. Okay. So this was very important. These velocity triangles, how to make these velocity triangles, the reference frame, the concept of reference frame, and how do we make the relative velocity vector, the absolute velocity vector, and the tangential velocity vector. This is very important. Okay. And also this equation of the torque. Okay. So if it is clear, then we will move to question number 2. Question number 2, it says for the turbo machinery, find the correct expression. So this is the expression for work, and we have to find the correct expression for a turbo machinery. So these terms are, you are familiar, right? C is absolute velocity. U is your tip velocity or the tangential velocity, and V is your relative velocity. Relative velocity of fluid with respect to blade. Okay. And we have to tell the expression for work. The expression for work we have already derived. Okay. The expression for work we have already derived. Where it is? Where it is? Okay. So here is the expression for work. Okay. So this is the expression for work. So this equation is in the terms of U and CW. Okay. So what we have to tell in terms of U and C and V. So basically we have to write CW in terms of absolute velocity and relative velocity, right? So I think that you can easily do. That is simple mathematics. Okay, simple mathematics. But just for the sake of solving, I will again quickly make the diagram. Okay, so sorry. This is blade tip velocity. Okay, and let us say this is the relative velocity of fluid with respect to blade. Okay, and this was your tangential velocity of blade, and this C is your relative velocity. Okay. So how do we define the vertical velocity? Vertical velocity component was defined as the component of absolute velocity along the tangential component. Okay. So the tangential component means along the u vector. Okay. So the C can be resolved like this. Okay. So the C, okay. So the C you can, so for C, the C, this is can be resolved in two components. One is CW, okay, and another one is radial component. So that is CR, okay, CR. In expression of work that we have derived, it was, sorry, per unit mass I'm writing, okay. So it was CW2 U2 minus CW1 U1, right? Okay. And we have to write this CW in terms of U and V. Okay. In terms of U and V. So how do we write this U and V? It is simply mathematics. Maybe I can write few steps. Okay. It is already derived in the lecture. Okay. We have to write the CW in terms of U, V, and maybe C, right? So how can we write? We need to eliminate this CW, right? So CW is basically uh, maybe if you see this triangle, sorry, if you see this green triangle, okay, then you can write it as C square is equal to CW square plus CR square. Okay, so CW square is basically C square minus CR square, right? Now you need to eliminate the CR. You need to eliminate the CR. Now for eliminating CR, what we can write? We can see this another triangle. Okay, we can see this another triangle. So in another triangle, you can write it as V square is equal to U minus CW square plus CR square. Correct? Okay. So from this equation, we can write as CR square is equal to V square minus U square minus CW square. Okay. And what else? Yes. And from the first equation, you can write as CR square is equal to C square minus CW square. Okay. CR square is equal to this. And from here, you have this. Okay. So now you can compare both of these equations. So you'll get CR square is equal to C square minus CW square is equal to V square minus U minus CW square. Okay. Correct. So from this equation, you can calculate CW, right? So let us expand this. C square CW square is equal to V square minus U square plus CW square, not plus this, minus CW square plus 2U into CW. Okay. So yes, these terms cancels out CW square both sides. Okay. So what you get? You get 2U CW is equal to C square minus V square plus U square. Okay. right? So UCW is equal to 1 by 2 C square minus V square plus VU square. Okay. So CW2 U2 will be 1 by 2 C2 square minus V2 square plus U2 square, and CW1 U1 will be equal to half C1 square minus V1 square plus U1 square. Okay. So now you can write C CW2 U2 minus CW1 U1 is equal to half C2 square minus C1 square plus U2 square minus U1 square and minus V2 square minus V1 square. Okay. And this is, and work is basically mass times CW2 U2 minus CW1 U1. So we just need to multiply by the mass flow rate. Okay. So C2 square minus C1 square plus U2 square minus U1 square minus V2 square V1 square. Okay. So this is the equation. So we have to tell which option is correct. Now you can easily tell. Option A is not correct. Option B, again not correct. Option C, not correct. Option D, not correct. All of these options are not correct. Okay, we will write our own option. W is equal to 1 by 2 C2 square minus C1 square plus U2 square minus U1 square minus V2 square minus V1 square. And we will take this answer. Okay. So I hope all of this is clear. If there is no doubt, then we can move ahead for the next question. So next question is question number 3. Question number 3 says, which of the following device is generally used to deliver low volume flow rate and high pressure rise per stage? So we have discussed both type of compressors, axial flow compressors as well as centrifugal compressor, and we have also discussed that centrifugal compressors provide high pressure rise at low volume flow rates. Okay, so the correct option is centrifugal compressor. Okay, so it is very simple. Okay, so I hope no doubt in this question. We can move to question number 4. Question number 4 says the blade angle for a centrifugal compressor blade with backward vanes is. Okay, so we have discussed two types of blades, right? Two types of blades, forward, uh, forward vane and backward vanes, right? For centrifugal compressors, we have discussed three types of blades. One is forward, one is backward, and another one is radial. So for radial, okay, so for radial, so in radial vanes, the fluid comes out radially. The fluid comes out radially. So this is the blade, let us say, and fluid will come tangentially. Okay, I am talking about the relative velocity. Okay, I am talking about the relative velocity. So it will come out radially. The relative velocity means v. Okay, so v2 it is along this radial direction. Okay, and if you draw, if you make the tangential velocity u, then you can see this angle is 90 degree. This angle you can see it is 90 degree. Okay, and if you make the absolute velocity, if you make the absolute velocity c vector, then okay, so this angle is alpha and this angle is beta. So for radial blades, this beta is equal to 90 degrees. Okay, and another type of blades are, so this is rotating like this. Okay, it is rotating like this. So it is rotating like this. Okay, so instead of going in this direction, in the direction of rotation, if fluid is going in opposite direction, then we say okay, it is in the backward direction. It is in the backward direction. Okay, so fluid is going like this, fluid is going like this, and blade is moving in this direction. Okay, blade is moving in this direction, so it is going in opposite direction. Okay, so the blade will be something like this. Okay, if I make the blade will be something like this. Okay, so here you can see this, here you can see this beta. This beta is basically less than 90 degree. Okay, this is backward vane, backward vanes, and another one is forward vane. And as you must have guessed, for forward vanes, beta is greater than 90, and flow goes in this direction, and this is the tangential velocity. Okay, and blade will be something like this. Okay, this is v, this is v. Okay, so what it is asking, outlet blade angle for a centrifugal compressor blade with the backward vane is, so with the backward vane is how much? This is less than 90. So it is less than 90. So correct option is option B, less than 90 degrees. Okay. If there is no doubt, then we can move to next question. Question number 5. Question number 5 says the centrifugal compressors are generally preferred for. So again, this is also discussed in the lecture that centrifugal compressors are very good choice for, small power plants, auxiliary power units, turboprops. Okay. So all of these options are correct. Okay. Now we move to question number 6. Question number 6 says which of the following compressor is suitable for large power requirement as well as large scale engine. So we know that axial compressors are well suited for large power requirement and in large engines. Okay, large scale engines, axial flow compressors. Moving to the next question. Question number 7. Which of the following, for centrifugal compressor, which of the following is function of an impeller? So let's read these options. Option A says to provide high velocity to fluid, which would deaccelerate in the moving blade passage. To provide option B, decrease the velocity of fluid, which would deaccelerate in moving blade passage. Option C, to provide rotational motion to oncoming fluid. Option D, to guide the oncoming fluid. So we know what impeller do. So impeller is basically rotating. Fluid comes, okay, and impeller blade basically imparts some kinetic energy to the fluid. Okay, fluid has some inlet, kinetic energy at inlet. Now this impeller is rotating, and this is, providing some, it is increasing the kinetic energy of the fluid. Okay, and that kinetic energy will be later converted into pressure energy. Okay, and the gaps between two impeller blade that keep on, increasing. So that basically deaccelerate the fluid. Okay, if you see the passage of moving blades, then what you observe that area of cross section that is increasing. So that increasing cross section area basically that will deaccelerate the fluid. Okay, and this impeller, since it is the basic purpose of the impeller itself is to increase the kinetic energy of the fluid. Okay, so it will provide high velocity to the fluid, and that will be will be converted into pressure energy later. Okay, so option A should be the correct option, right? And to option B says to decrease the velocity of fluid. No, this is not correct option. Option C says to provide the rotational motion of the oncoming fluid. Well, yes, it is providing some rotational motion because the fluid is coming axially, and then it is rotating, and then at the exit it is going, radially outward. Okay, so in between, yes, it was rotating, but that is not the purpose of the centrifugal compressor. Okay, the purpose of the centrifugal compressor is to you know to increase the pressure. And how that pressure is increased? First of all, we increase the kinetic energy of the fluid. Okay, how? By the rotating impeller, and that impeller pushes that fluid. Okay, that increase the kinetic energy, and that kinetic energy later converted to pressure energy. So that is the correct option. And to guide the oncoming fluid, no, that is not the purpose of impeller. Basically, for that we have another component, that what we call inlet guide vanes, right? So this was question number 7. I hope this is clear. Now moving to question number 8. Question number 8 says, in case of centrifugal compressor with inlet guide vane. Okay, so inlet guide vane. Which of the following statement is correct for the radial vanes? So we have already discussed 3 types of vanes, right? Radial, forward, and backward. So for radial vanes, we have seen that beta is equal to 90 degree. Okay, beta 2 is equal to 90 degree for radial vanes. Now what about beta 1? So beta 1 is equal to also 90 degree because we are using inlet guide vane, and purpose of inlet guide vane itself is to make the fluid flow direction radial. Okay. So I think this is also clear, right? Again, if there is no doubt, then we can move to the next question. Okay. Question number 9. So question number 9 says a centrifugal compressor has a pressure ratio of 4:1 with an isentropic efficiency of 80% when running at 15,000 revolutions per minute and inducing air at 20 degrees Celsius guide vanes. Guide vanes at inlet gives the air a pre-whirl of 20 degrees to the axial direction at all radii. Okay. And the mean diameter of I is 250 mm. The absolute air velocity at inlet is 150 meter per second. At exit, the blades are radially inclined and the impeller tip diameter is 590 mm. Calculate the slip factor of compressor. Okay. So it is given that compressor has a pressure ratio of 4:1. So pressure ratio, I think that should be clear by the name itself. So pressure ratio is the ratio by which the pressure is increased. Okay. If the pressure at inlet was 1 bar, then at outlet it should be 4 bar. Okay. That is pressure ratio. Isentropic efficiency we have already discussed, right? Isentropic efficiency of compressors we have discussed, right? When we are discussing Breton cycle, right? Running at 1500 revolutions per minute. So that is basically omega, right? Inducing air at 20 degrees Celsius. So this is temperature at inlet. Okay. And the inlet guide vane gives air a pre-whirl of 20 degrees. So this 20-degree basically mean that it is not radial. Okay. So it has some CW1 that is not 0. Okay. To the axial direction at all radii, and the mean diameter of I is 250 mm, absolute velocity of air at inlet. So this is C1 is basically 150 meter per second, and the exit blades are radially inclined at impeller tip diameter is something, and we have to calculate the slip factor. Okay. So slip factor, I hope you know what is slip factor, right? Because we have to calculate the slip factor. So you should know what is slip factor, what we have to find. So slip factor is basically CW2 divided by U2. Because in the ideal case, we assume that this fluid is coming out radially. Okay, this fluid is coming out radially. So this means that that this is absolute velocity and this is tangential velocity U2. This is C2. So now we can see it is coming out radially. Okay, right? So in this case, you can see that sorry. If it is coming out radially, so this means that relative velocity is radially outward. Then absolute velocity will be this. Okay. So what I mean is I am repeating the blade vanes. Okay, the blade will be radially radial. Okay, so since the fluid will be uh, moving over the blades and blades are radial, so that relative velocity of the fluid will be in the radial direction. Okay, so u2 is in the radial direction and u2 is tangential velocity, and this is your absolute velocity. And if you make the components, then you can easily see that this absolute velocity c can be resolved in two components. So the viral component, that is cw2, that will be equal to u2, and the radial component cr2, that will be equal to v2. Okay, so this is for the ideal case, but we know that this cw2 and u2, they will not be equal in the real case. Okay, for ideal case they are equal, but in the real case they are not equal. So that ratio is basically defined by slip factor. Okay, so slip factor is basically cw2 divided by u2. Okay, so this slip factor we have to calculate, right? So how do we calculate the slip factor? We need two things, u2 and cw2. So u2 can be easily calculated from the diameter or the radius, and this omega we have 15,000 per revolutions per minute, and radius is also given. Only what we need is cw2. Okay, so let's try to calculate that. Pressure ratio is given. Okay, so pressure ratio is given 4:1. Okay, and isentropic efficiency is also given. Isentropic efficiency is given. Okay, Nita isentropic is 80%. So this means this is not isentropic. If it was isentropic, then in case of isentropic compression, what will happen? You know, from expression for isentropic process, right? What we know, that T2 will be equal to T1 times P2 by P1 to the power gamma minus 1 by gamma, right? So T1 in our case is T1 temperature at inlet. So T1 is what? 20 degrees Celsius. So 20 degrees Celsius. So it will be 20 degrees Celsius. We need to convert in Kelvin. So 273 times 4 to the power gamma, let us say gamma. Okay, gamma we will take 1.4 SI units. Okay, so it will be 0.4 divided by 1.4. And if you calculate this value, I already have the answer, so I am writing it directly. If you calculate and if you get some different value, then please let me know. What I have is 435.4 Kelvin. So this is temperature at exit in the case of an isentropic process. If this process was an isentropic process, then temperature would have been 435.4 Kelvin, but it is not isentropic. Why? Because there is 80% isentropic efficiency, right? So isentropic efficiency, if isentropic efficiency is given, then actual temperature rise will be, okay, the actual temperature rise will be more than that, right? So it will be isentropic temperature rise, isentropic temperature rise divided by isentropic efficiency. So what is isentropic pressure rise? What is isentropic pressure rise? So how much pressure has increased? T2 minus T1 divided by isentropic efficiency, right? So this will be, let us make it S. This is isentropic temperature rise. So T2 minus T1, this is actual temperature rise. Okay. So this will be 435.4 minus 20 plus 273. divided by isentropic efficiency is 80%. Okay, so T2 minus T1 will be, again, we need to calculate this value, and if you calculate this value, this should come out to be 142.4 divided by 0.80, so that should be equal to 178 Kelvin. Okay, so this is the temperature rise, T2 minus T1. Okay, now you have temperature rise, then you can calculate power input requirement, right? So power input, if you want to write, power input per unit mass, what it will be? It will be Cp delta T, right? So Cp, let us take the standard value of Cp. Okay, I am again assuming, if it is not given, right? So we are assuming 1.005 kilojoule per kg Kelvin. Okay, 1.005 times temperature rise delta T. So this is 178 Kelvin. So if you calculate this value, this will come out to be 178.9 kilojoule. Okay, correct. Okay, we have got the power. Okay, now if you want to write the U2, okay, if you want to write, sorry, U1, then it will be angular velocity times radius. So angular velocity is given, omega is given 15,000 revolutions per minute. So in radians per second, it will be times 2 pi divided by 60 radian per second. So this is omega, right? And radius, is the radius given? Well, radius is not given, but mean diameter is given. Okay, so you can take the radius, you can take the mean radius as half of this mean diameter. Okay, so you can write U1 is equal to omega 15,000, 2 pi by 60 times 250 into 10 to the power minus 3. Okay, that was in mm, divided by 2. Okay, so this will be blade velocity, right? So U1 you get as, if you calculate this value, then it should come out to be 196 point, sorry, 196.4 meter per second. Okay, Now we will try to make a diagram, velocity triangle. So if it was a ideal blade, then absolute velocity will be along the you know, radius, but it has some angle of prevail. Okay, right? So if it was ideal case without any prevail, okay, so at inlet, if you make without prevail, then the velocity triangle will something will be like this, right? So this is blade velocity u, and this is relative, sorry, the absolute velocity will be along this direction, u1 c1. This will be your relative velocity v1, but since it has some whirl, okay, so what will happen, this c will not be along the radial direction. Okay, so it will be something like this. Okay? This is the actual case. So with whirl. Okay, sorry. It will not be along radius. There will be some angle with this direction. Let us say some angle. Okay. Okay, so this is angle of prevail. This is how much? 25 in our case. So from here you can calculate this CW1. Okay, you can calculate this CW1. So this CW1 will be C times C1 times C1 times sine of 25 degrees Celsius. Sorry, 25 degrees angles. Okay. And C1 is absolute velocity, and C1 is absolute velocity at inlet, and so absolute air velocity at inlet is given 150 meter per second. Okay, so C1 is 150 meter per second. So 150 meter per second times sine 25. Again, you can calculate this value, and if you calculate this value, then it will come out to be 63, sorry, 63.4 meter per second. Okay. So this was at the inlet. Now at outlet. Now let us write at exit. We will do the same thing. Okay. You have omega. Omega is 15,000 times 2 pi divided by 60 radian per second. We need to calculate U2. So U2 will be R2 times omega. So do we have R2? Let's see. Do we have R2? Yes. Impeller tip diameter is 590 mm. Okay. 590 mm. So R2 is 590 mm by 2, right? So 590 by 2 times 10 to the power minus 3 times this omega meter per second. This will be your U2, tangential velocity at outlet, tangential velocity of blade, right? Now, if you calculate this value, it will come out to be U2 is equal to 463.4 meter per second. So please check this value. Okay, I already had this answer, so I'm writing it directly. You calculate yourself and check if you are getting the same velocity or not. If there is some difference, then please let me know. Okay, this is U2. For ideal case, okay, for ideal case, it should come readily out. Okay, so if it is given or not, radially inclined. It is given radially inclined. Okay, so flow will come out radially. So radially means blade is inclined in the radial direction, means blade is something like this, right? Blade is something like this, and fluid will be moving over this blade. So the relative velocity will be along this blade. So radial velocity is along, sorry, the relative velocity is along the radial direction. And this is the blade tip velocity U2, this is V2. So absolute velocity at outlet will be something like this. Now, if you draw the components of the absolute velocity, then this is CW2 and this is CR2. Okay, so you can clearly see that CR2 is equal to V2 and CW2 is equal to U2, right? So U2 you have already calculated. U2 you have already calculated here. So this is 463.4 meter per second. Okay. Now you have CW at inlet as well at exit, and also you have U1 and U2. So you can write power input, right? Power input per unit mass flow rate. Okay. It will be what? CW2 U2 minus CW1 U1, right? And this thing you have already calculated. Okay, power you have already calculated 178.9 kilojoule. Okay, so 178.9 kilojoule, that will be equal to C2 is just calculated. Okay, C2 and U2 are both are equal, so it will be 463.4 squared, right, minus C1. How much is C1? C1 is 63.4. 63.4 times U1. How much is U1? U1 is 196.4. 196.4. Okay. So instead of kilojoule, let me write in joules. Okay. This would have been in the ideal case. This would have been in the ideal case. when slip factor is 0. So this case is when, sorry, slip factor is 1. But in real case, okay, but in real case, this will not be correct. So in real case, it will be 178.9 into 10 to the power 3 joule equal to, I think I should write this comment somewhere else. No. Sorry. U2 minus CW1 U1. Okay. So this, whatever I have written here, this thing, this will be in ideal case. Okay. In real case, CW2 will not be equal to U2. Okay. So in real case, let us say we have CW2 dash, CW2 dash. Then in that case, the power requirement will be U2. What is U2? U2 is 463.4 times CW2 prime. This is the real or the actual velocity component, minus 63.4 times 196.4. Okay. So from here you can calculate CW2 dash. Okay. CW2 dash, if you calculate from here, then you will find that this value is coming out to be 412.9 meter per second. Okay, this is the actual. And you know that how do we define the slip factor? Slip factor is defined as actual viral velocity component, right, divided by U2. Okay, or CW2 divided by. Okay, this is the theoretical. So if you substitute the values, this value just you calculated 412.9 meter per second, and CW2 that is equal to U2, that is 463.4. 463.4. If you calculate this value, it will come out to be 0.89. So this is the slip this is the slip factor. This is the slip factor. Okay. Okay. Because in the real case, CW2 is not equal to U2. So that ratio is defined as slip ratio. Okay. So I hope this is clear. Okay. The only thing is that you should know how to make the velocity diagrams. How do you make the absolute velocity vector? How do you make the relative velocity vectors? These are very important points. Okay. So the relative velocity vectors, that is along the blade. Okay. That is tangent to the blade. Okay. And U, that is the tangential velocity that we are calling, that is basically that blade tip velocity. Okay. And that is given by angular velocity times radius. Okay. So I hope this is clear. Okay. Now we can move to the next question, or probably you can note down this question and you can try to solve yourself. And if there is any doubt, then of course we can discuss in the next session. But anyway, first let us read this question, what it is saying. Question number 10 says air flows from atmosphere at pressure 101.3 kilopascals. Okay. The temperature is 288 Kelvin into a centrifugal compressor with radial blades. Okay. So it has radial blades, right? At exit of impeller, and without any swirl at inlet. So what it is saying that blades at exit are radial. Okay, and there is no swirl at inlet. Okay, so there is no swirl at inlet. Fine. So this means there is no variable velocity component at inlet. So CW1 is equal to 0, right? Then it says that compressor wheel has 18 blades. It has 18 blades. Fine. And it turns at 15,000 RPM. So this is your angular velocity. The exit radius is R2 is equal to 26 centimeter, and the inlet hub radius is 8.5 centimeter, and shroud radius is 17 centimeter. The total to total efficiency is 0.79. We have to find the power required, assuming that mass flow rate is okay. So mass flow rate is given m dot is equal to 8 kilogram per second, and it is saying that use the Stanage formula to find the velocity, sorry, the slip coefficient, and find the stagnation pressure ratio. Okay, so most of the things we have already discussed in the previous questions, right? For example, if the radius is given, angular velocity is given, then you can calculate the tip velocity, or u, right? U1 and U2 you can calculate. Slip velocity, sorry, slip coefficient we discussed. Now it is saying that we have to use Stanage formula. So it has already been discussed in the lecture. I will just write it again. So Stanage formula or slip coefficient is sigma is equal to, okay, sigma is basically slip coefficient, 1 minus 0.63 pi divided by n. Okay, so this is sigma is slip coefficient, n is the number of blades. That is 80 in our case, right? 18 blades are right. Okay, 18 blades. Fine. So from here you can calculate sigma, right? So from here you can calculate sigma, and sigma will come out to be, I'm writing the value, it will come out to be 0.89. So now you have slip factor. You have slip factor, and it is given that blades are radial at exit, right? So CW2, okay, so CW2 and U2. So relation between CW2 and U2 will be given by this slip ratio, right? As we discussed in the previous question. So CW2 by U2 is equal to sigma. Okay. So U2 you will have from where? From the because you have radius and you have angular speed. So you will get angular speed times radius at exit will be equal to your U2. And slip velocity, slip coefficient is given. So you will get CW2, right? And other things are also given. Mass flow rate is given. Anything new? So I think everything else is same. We have already discussed, right? Then you can easily proceed. Okay. So I will write the answer directly. Okay. Everything is given, right? 15. This is given. This is given. This. I will write the answer. You please try to solve yourself. If there is any problem, then we can solve in next session. Okay. What we have to calculate? Calculate the power required. Okay. Option A, power required. And this will be 1187.6 kilowatt. Option B, it is asking to find the stagnation pressure. Stagnation pressure ratio. Stagnation pressure ratio. Stagnation pressure has already been discussed in the lecture, I think. And the stagnation pressure ratio that I have, it is given to be 3.29. Okay. So how do we define the stagnation pressure? Let me. Basically we define the stagnation temperature. So stagnation temperature means if we bring the fluid to the rest isentropically, then that temperature will be called your stagnation temperature. Okay. And what else? Yes, this efficiency is also given. Okay. So this efficiency you can use. So this means that some part is being lost. Some part of work is being lost. Okay. So Ws will be equal to this neta times W. Okay. And stagnation temperature will be at exit. Uh, okay, I think equal to plus Ws by Cp. So from here you'll get this thing. And your pressure ratio will be equal to the power gamma minus 1. Okay. And gamma you can assume 1.4. Okay. So please substitute these values and you will get the answers, I think. If there is any problem, then we will solve it in the next session. Okay. So we will stop here, but before we leave, important thing we should note here is that velocity triangles are very important for solving any turbo machinery problem. Okay. And all the formulas that you are using, that those are also derived from the velocity triangles only. So in case if you forgot any formula, then if you know how to draw these velocity triangles, then you can easily derive those formulas. Okay. So these velocity triangles should be very, very clear. Okay. So thank you. We will stop here and we will meet in the next session. Okay. Thank you.